Hello everyone, my name is Amir Nodehi and I'm going to present you Sabet, an out-of-GPU memory graph processing framework. This is a joint work with my advisor Dr. Zhijia Zhao and Dr. Rajiv Gupta. Graph is a data structure consisting of nodes and edges. Nodes model entities and edges model relationships between them. Graphs have been widely used in many application domains, such as social network analysis, recommendation systems, biomedical research, and many others. One popular way to implementing graph applications is based on the vertex-centric programming model, where computations are defined from the view of a vertex. On the right is a vertex function for the connected component problem. The function goes through each neighbor of that vertex and checks if its value is less than the value of the neighbor, and if so, it propagates its value to the neighbor. During the graph processing, the vertex function is applied to every vertex of graph iteration by iteration until the values of all vertices become stable. With thousands of cores, GPUs offer massive parallelism for vertex-centric graph processing. There have been a series of GPU-based graph processing systems developed, including Kusha, Guanrock, Tiger, and many others. Most of these systems assume the input graph can fit into the GPU memory. However, in practice, real-world graphs tend to grow in many applications. For example, the size of web graphs increases as more web pages are crawled. In social networks, as new users join and build new relations, the graphs become larger and larger. Once the input graphs become too large to fit into the GPU memory, either we deny processing the graphs or we have to switch to out-of-GPU memory graph processing. One basic approach to process oversized graphs is graph partitioning. It first divides the nodes of the graph into partitions, along with their outgoing edges. Then, during each iteration of the graph processing, it loads the graph into the GPU memory, partition by partition. Usually, the node data is stored in GPU memory while the graph topology is stored in host memory. This animation shows partitioning-based graph processing. However, the problem with this approach is that the graph loading from CPU to GPU becomes the performance bottleneck. In fact, it dominates the total execution time. To address this issue, existing graph systems try to hide the data transfer cost by overlapping it with the graph computation. Unfortunately, the benefits of this optimization are limited. As shown in this figure, for many graph applications, the cost of data transfer is significantly higher than the graph computation time. This means the data transfer cost we can hide is very limited. Can we directly reduce the data transfer cost? The answer is yes. Our key observation is that in most iterations of the graph processing, only a small ratio of vertices are active. That is, only these vertices and their edges need to be processed. This table shows the average ratio of active edges across all iterations with 3 graph algorithms on 2 real-world graphs. So, the question is, can we only load these active parts of the graph? Essentially, this requires extracting a subgraph from the original graph. As the active parts of the graph change over iterations, the conventional wisdom is that the subgraph is too expensive to generate. In this work, we challenge this conventional wisdom and demonstrate that the active subgraph can be efficiently generated with a group of novel techniques. These include a concise subgraph representation called sub-CSR, a highly parallel subgraph generation algorithm, and a GPU-accelerated implementation. With these techniques, we make the overhead of subgraph generation significantly less than the benefits of reduced data transfer. As a consequence, instead of paying extra cost, the subgraph generation is able to bring significant performance benefits. Next, let me briefly show the basic ideas of these techniques. Many graph systems, especially those based on GPUs, use a compact graph representation called CSR, which represents a graph with a vertex array and an edge array. Each value in the vertex array shows the beginning position of the edges belonging to that vertex. To represent a subgraph extracted from a CSR formatted graph, we introduce the sub-CSR format, which is similar to CSR. The main difference is that the vertices in the sub-CSR format use two arrays. One indicating the vertex IDs in the original graph, and the other indicating offsets of edges, just like the vertex array in the CSR. As you can see, the structure of sub-CSR is simple and concise, introducing very little space overhead, and more importantly, it can be quickly constructed. Here is our algorithm for constructing the sub-CSR based on the activeness labels. It consists of 6 basic steps, including 3 stream compact operations, 2 prefix sum operations, and 1 value reset operation. For the time limit, I will not go over them in detail, but the key is that all these operations are highly parallelizable. To effectively explore this parallelism, we implement most of the steps on GPU. In fact, only the last step is performed on the CPU. The use of GPUs can greatly accelerate the sub-CSR construction. Now, let's take a look at the cost. Here, we compare the sub-CSR construction cost plus the new data transfer with original data transfer time. As you can see, even including the sub-CSR construction cost, the total cost is still much less than the original data transfer cost, which confirms overall benefits of our approach. Besides subgraph generation, we also explored asynchronous graph processing, which has been proved as a valid optimization for many graph applications. In specific, we iteratively process a loaded subgraph in the GPU memory until its values are converged before we load the next subgraph. We found that this asynchronous processing tends to reduce the global graph iterations, thus reducing the needs for generating subgraphs and loading them into GPU memory. Finally, let's take a look at the evaluation results. Here we compare our approach with not only the partitioning-based approaches, but also the unified memory-based approach. The unified memory is a recent GPU feature that transparently transfers data from CPU to GPU on demand at the memory page level. Here are the performance results. Let's take the first row as an example, which runs single source shortest path on the friend-served graph. The basic partitioning-based approach, or baseline, takes 68 seconds. After applying overlapping optimization, we get 1.6 times the speed up. With unified memory, the performance becomes even worse due to the overhead of page fault handling. In comparison, Subway Sync and Subway Async show much more speed up over the baseline thanks to their subgraph generation and asynchronous processing techniques. You can find more results in our paper. That's it. I hope you enjoyed this presentation. You can find me on Slack or by email. The source code will be available soon in this GitHub repository. Thank you. Bye.